A supermassive black hole sits at the heart of galaxy GNZ11, one of the most distant galaxies ever observed. This black hole existed when the universe was only 430 million years old. Its mass equals millions, possibly billions of times the mass of our Sun. That should be impossible. Let's walk through why. Black holes form when massive stars collapse at the end of their lives. A star needs to be at least 20 times more massive than our Sun to create a black hole when it dies. The resulting black hole typically weighs 10 to 100 times what our star weighs a stellar mass black hole. From there, it can grow by consuming gas, dust, and other stars. But this process takes time, billions of years to reach supermassive status through gradual accumulation. The physics of matter falling into black holes imposes strict limits on growth speed. When matter falls toward a black hole, friction heats it to millions of degrees. This superheated material radiates energy intensely. That radiation pushes against infalling matter, creating outward pressure that counteracts gravity. This effect, called the Eddington limit, sets a maximum rate at which black holes can consume matter. Even if a black hole formed immediately after the Big Bang and consumed material continuously at the maximum possible rate, it couldn't grow to billions of solar masses by 430 million years. The math doesn't work. The physics doesn't allow it. Yet there it was. Webb detected extremely dense gas surrounding the black hole, a signature of rapid accretion. The black hole was actively feeding, pulling matter inward at tremendous rates. Spectral analysis revealed patterns that only appear near supermassive black holes consuming gas broad emission lines, specific wavelength features that confirm both the black hole's presence and its enormous mass. This galaxy isn't unique. Webb has discovered multiple supermassive black holes in the early universe. Some appear even more massive than expected for their cosmic age. Each discovery deepens the mystery of how these objects grew so large so quickly. Several theories attempt to explain this, though none are fully satisfying. One possibility involves dark stars' theoretical objects powered by dark matter annihilation rather than nuclear fusion. If dark matter particles and antiparticles collide and annihilate inside a massive star, they could release enough energy to support the star against gravitational collapse. These dark stars could grow to millions of times the mass of our Sun before eventually collapsing directly into massive black holes, providing a significant head start on growth. Nobody has ever observed a dark star, but the physics is theoretically sound. If they existed in the early universe when dark matter was denser, they could solve the supermassive black hole problem elegantly. Another theory suggests that in the dense early universe, gas clouds could collapse directly into massive black holes without forming stars first. If conditions were right, if the gas was hot enough to prevent fragmentation but dense enough for gravitational collapse, a cloud containing 100,000 solar masses might compress straight into a black hole of equivalent mass. This process, called direct collapse, has never been observed, but mathematical models show it's possible under specific conditions. The early universe might have provided those conditions more frequently than the modern cosmos does. A third explanation involves collisions and mergers. If smaller black holes merged frequently in the crowded early universe, they could build up mass faster than accretion alone allows. Gravitational wave detectors like LIGO have confirmed that black hole mergers occur regularly in the modern universe. Perhaps they happened far more often in the past when galaxies were closer together and interactions more common. Each merger would create a larger black hole. Multiple mergers in quick succession could build supermassive black holes on accelerated timescales. The problem is that mergers still take time. The black holes must spiral together, radiating gravitational waves. Even with frequent mergers, reaching billions of solar masses in 430 million years seems challenging. What makes these black holes especially important is their role in galaxy evolution. Black holes don't sit passively at galactic centers. They blast out enormous amounts of energy as matter spirals inward. This radiation heats surrounding gas and can either trigger star formation by compressing clouds or shut it down completely by heating gas beyond the point where it can collapse. Supermassive black holes help regulate how galaxies grow. Finding them so early means they influence cosmic evolution from nearly the beginning. Their presence could explain some of the unexpected galaxy properties. Webb keeps discovering the unusual brightness, the rapid star formation, the accelerated assembly of massive structures. But before these black holes existed, something even stranger might have burned in the primordial darkness. Scientists detected something peculiar in the spectrum of galaxy GSC 12. The light contained an extreme imbalance of nitrogen compared to oxygen, a ratio that measured completely off the charts compared to any normal stellar population. Stars don't naturally produce that chemical signature through ordinary fusion processes. Stellar explosions don't create it either. But theoretical models predicted exactly this signature from a type of star never observed: primordial monster stars thousands of times more massive than our Sunday. These theoretical giants would have formed in the very early universe from clouds of pure hydrogen and helium. No heavy elements existed yet to contaminate the gas. The first generation of stars, called Population 3, consisted entirely of the lightest atoms. Without heavy elements to help cool the gas through radiation, these clouds collapsed into much more massive stars than form today. A monster star might weigh 1,000 to 10,000 times what our star weighs. It would burn incredibly hot, with core temperatures reaching billions of degrees. Its core would fuse helium into carbon at ferocious rates. The carbon would then capture additional helium nuclei through a process called the CNO cycle, carbon-nitrogen-oxygen cycle, producing vast quantities of nitrogen. These stars would burn brilliantly for perhaps only a few million years before exhausting their fuel. When they died, they wouldn't explode like normal supernovae. They would collapse directly into massive black holes, leaving no remnant. But during their brief lives, they would spew nitrogen-rich material into space through powerful stellar winds. That material is what Webb detected in GSC 12, the chemical fingerprint of monster stars that lived and died billions of years ago. The nitrogen they produced remained in the galaxy, mixed with later generations of normal stars, creating the unusual spectrum astronomers observed. This discovery provides the first clear evidence that Population 3 monster stars actually existed. For decades, they remained purely theoretical. Mathematical models showed they should form under primordial conditions, but nobody had ever detected their chemical signatures in real galaxies. Webb changed that, confirming predictions and opening new questions about the early universe. The implications reach far beyond confirming a prediction. Monster stars help solve the supermassive black hole problem we just discussed. If stars this massive collapsed into black holes weighing thousands or tens of thousands of solar masses, those black holes would have a huge head start on growth. They could reach supermassive status much faster than black holes formed from normal stars. Monster stars also contributed to reionization, the period when the first sources of light began ionizing the hydrogen gas that filled space. Their intense ultraviolet radiation would have stripped electrons from atoms across vast regions, making the universe transparent to light. This process transformed the cosmos from an opaque fog into the clear medium we observe today. Additionally, these stars produced the first heavy elements. Every atom of carbon, oxygen, and nitrogen in the early universe came from stellar interiors. Monster stars forged these elements faster and in greater quantities than normal stars could, seeding the formation of subsequent star generations that could form planets and, eventually, life. The universe's largest stars burned at the beginning, not now. They were brief, but essential architects of everything that followed. Yet even these giants were just individual objects. The universe's true scale reveals itself in its largest structures. The universe isn't distributed evenly. Galaxies cluster along threads of dark matter that stretch tens of millions to hundreds of millions of light years across space. These filaments connect at massive intersections where thousands of galaxies accumulate. Between the threads lie voids, vast empty regions where almost nothing exists. This pattern is called the cosmic web. It's confirmed as the largest structure in the universe, a scaffolding of dark matter that pervades the entire observable cosmos, integrating all gravitationally bound structures into one interconnected network. The web formed from tiny density fluctuations in the early universe. Regions that were slightly denser than average had slightly more gravity. They pulled in more matter, which increased their gravity further. The process amplified over billions of years, creating denser and denser regions connected by streams of infalling material. Think of it like water flowing downhill into valleys. The valleys represent regions of higher dark matter density. The streams represent filaments where matter flows from one concentration to another. Over cosmic time, these streams become highways of galaxies traveling along gravitational corridors. Dark matter provides the scaffolding. It comprises roughly 85% of all matter in the universe, confirmed by gravitational effects on visible matter. Dark matter doesn't emit light or interact with electromagnetic radiation. We detect it only through its gravity, through how it bends light, how it affects galaxy rotation curves, how it holds clusters together. Where dark matter concentrates, normal matter follows, drawn by gravity into the densest regions. Scientists map the cosmic web by surveying millions of galaxies and measuring their positions in three-dimensional space. Patterns emerge clearly. Galaxies line up along specific directions. They cluster at nodes where multiple filaments intersect. They avoid regions between filaments, creating the vast voids we mentioned earlier. The distribution reveals the underlying dark matter structure with remarkable clarity. Our local group, which includes the Milky Way and Andromeda, sits on a filament connecting the Fornax cluster to the Virgo cluster. This filament stretches approximately 110 million light-years across. Light from some parts of our local structure left its source when dinosaurs walked on Earth. That's how vast these structures are. The largest concentrations occur where filaments meet. These intersections become galaxy clusters, the most massive, gravitationally bound objects in existence. A typical cluster might contain 100 to 1,000 galaxies with a total mass of 100,000 billion times the mass of our Sunday. They represent the high-density nodes of the cosmic web, the places where everything comes together. Material flows along filaments toward these clusters. Galaxies that started out isolated drift along the threads and eventually join cluster populations. As they travel, they interact with other galaxies. Collisions occur. Mergers happen. Gas gets stripped away by the hot plasma filling space between galaxies. These environmental effects transform spiral galaxies into elliptical ones, changing their properties fundamentally. Recent observations detected dark matter directly on filaments for the first time. Using gravitational lensing, the bending of light around massive objects, scientists observed how light from distant galaxies bent around invisible mass concentrations along cosmic web threads. The measurements confirm that dark matter really does line the filaments, not just concentrate at nodes. Dark matter hangs throughout the web's structure, creating a continuous network spanning the observable universe. But Webb revealed something even more extreme, specific concentrations that challenge the limits of what the web can build in the available time. Astronomers using Webb data discovered a massive chain of at least 20 closely packed galaxies. They call it the cosmic vine. It swoops through space in a bow shape, stretching more than 13 million light-years long and approximately 650,000 light-years wide. For comparison, our entire galaxy measures only 100,000 light-years across. This structure is 130 times longer than our galaxy is wide, an almost incomprehensible scale. All 20 galaxies showed a redshift of roughly 3.44, meaning their light traveled between 11 and 12 billion years to reach us. They existed when the universe was only a few billion years old. The vine formed during an era when such large structures shouldn't have had time to assemble. What makes the cosmic vine remarkable is its size compared to other galaxy groups at similar distances. It's significantly larger than anything else discovered at this cosmic epoch. The structure appears to be in the process of becoming a galaxy cluster, one of the universe's most massive formations. Current mass estimates place the vine at approximately 260 billion solar masses. That's already enormous, but it's still growing. Galaxies continue to drift along the filament drawn by the combined gravity of the structure. Eventually, over the next several billion years, these galaxies will merge into a unified cluster. What puzzles researchers is the state of the two largest galaxies in the vine. When scientists analyzed the wavelengths of light these galaxies emitted, they found that star formation had almost completely stopped. The galaxies are classified as quiescent. They're no longer actively producing new stars. This is highly unusual for the early universe, Most galaxies at this distance are still forming stars vigorously, consuming their gas reserves to build new stellar populations. Finding large galaxies that have already used up their gas reserves suggests something dramatic occurred. One possibility is that these galaxies resulted from recent mergers. When galaxies collide, they can trigger massive bursts of star formation that consume available gas in a relatively short period. The collision heats gas to extremely high temperatures. Hot gas doesn't collapse easily to form stars. It can also be expelled from the galaxy entirely by the energy released during the merger, leaving behind a galaxy full of existing stars, but depleted of the raw material needed to build new ones. Another explanation involves the environment. Galaxies in dense structures experience different conditions than isolated galaxies. They pass through hot plasma, filling the space between galaxies. This plasma can strip away their gas through a process called ram pressure stripping. Imagine sticking your hand out of a car window at highway speeds. Air resistance pushes your hand backward. Gas in galaxies experiences similar forces when moving through the hot medium between galaxies, and that gas can be torn away completely. The cosmic vine represents just one example of unexpected large-scale structure in the early universe. Webb keeps finding massive concentrations that formed faster than models predict. Each discovery adds evidence that something about early structure formation proceeds more efficiently than standard theory allows. These enormous structures don't exist in isolation. They're part of a much larger population of galaxy groups that Webb has catalogued across cosmic time. A team of astronomers compiled the largest and deepest sample of galaxy groups ever observed. They detected 1,678 galaxy groups and protoclusters spanning from 12 billion years ago to approximately 1 billion years ago. This catalog maps cosmic family trees from near the beginning. Each galaxy group represents a collection of galaxies held together by gravity. They're smaller than massive clusters, but larger than individual galaxies. Think of them as neighborhoods in the cosmic web, distinct communities connected by the larger structure, but maintaining their own local gravitational identity. What makes this catalog revolutionary is its depth. Previous surveys could only glimpse parts of this evolutionary sequence. They might catch groups at one cosmic epoch or another, but they couldn't trace continuous development across billions of years. Webb changed that. Its infrared sensitivity allows detection of galaxies 1 billion times fainter than what human eyes can see. That's not an exaggeration, 1 billion times fainter. This sensitivity opens windows into cosmic history that were previously completely opaque to observation. The catalog reveals how galaxy groups evolve over time. In the early universe, groups appear chaotic. Galaxies show irregular shapes. Star formation proceeds vigorously. The structures are loose, still assembling, not yet settled into stable configurations. As time progresses, the groups become more organized. Galaxies develop symmetrical shapes like spirals and ellipses. Star formation slows down through a process called quenching. The groups grow more compact as gravity pulls members closer together. Eventually, many groups merge into larger clusters. This evolution reflects broader processes shaping cosmic structure, dark matter halos accumulating over time, small halos merging into larger ones, gas heating as it falls into these halos, supermassive black holes blasting energy into surrounding space. All these effects combined transform the properties of galaxies and the groups they inhabit. Scientists can now track individual galaxy populations through multiple evolutionary stages. They identify galaxies at one distance, then look for similar galaxies at other distances to see how that population changed. This creates a narrative of cosmic history, showing how different types of galaxies emerged and evolved over billions of years. The catalog also reveals environmental effects clearly. Galaxies in dense groups behave differently than isolated field galaxies. Group members experience more frequent interactions, they collide more often, their gas gets heated by the hot plasma filling space between them. These environmental factors accelerate evolution, transforming active star-forming galaxies into quiescent ones faster than would happen in isolation. One particularly striking finding involves the transition from chaotic to organized. The shift occurs fairly rapidly in cosmic terms over just a few billion years. Early groups show high star formation rates and irregular morphologies. Later groups show low star formation and regular shapes. The transformation coincides with the era when dark matter accumulation shifted from rapid growth to slower consolidation. This correlation suggests dark matter evolution drives the visible changes we observe in galaxy populations. This catalog provides observational evidence for theories about how structure forms in the universe. It confirms predictions about halo assembly. It validates models of environmental quenching. It demonstrates how the cosmic web organizes matter on the largest scales. Yet even with nearly 1,700 groups catalogued, vast regions of space contain nothing at all. Between the filaments of the cosmic web stretch enormous empty regions called voids. These spaces contain almost no galaxies, almost no stars, almost no matter of any kind. They extend for hundreds of millions of light years in every direction, representing the largest continuous volumes of emptiness in the universe. The voids aren't completely empty. A few small galaxies drift through them, isolated and alone. Sparse filaments of dark matter thread through the edges. But compared to the dense regions where galaxy clusters form, voids contain less than 10% of the average matter density of space. Imagine standing in the middle of a void. Look in any direction and you would see darkness extending for tens of millions of light years before encountering the nearest galaxy. The void would appear as a cosmic desert, an immense region where structure formation failed to occur. Voids formed through a process opposite to how clusters form. Regions that started slightly less dense than average had slightly less gravity. Matter flowed out of these regions toward denser areas. This decreased their density further. The process continued for billions of years, creating vast underdense regions while concentrating matter along the boundaries. These boundaries are where filaments exist. Matter drains from voids and accumulates on the walls separating them. Over time, voids grow larger as more material evacuates toward the edges. The cosmic web evolves by expanding voids and compressing filaments, creating an increasingly structured pattern. The largest known void stretches approximately 1 billion light-years across. That's roughly 1% of the observable universe's diameter. Light takes 1 billion years to cross it. If you started at one edge and traveled at the speed of light, you would spend 1 billion years crossing nothing but empty space before reaching the other side. Scientists study voids because they provide clean laboratories for understanding cosmic expansion and dark energy. In dense regions, local gravitational effects complicate measurements. Galaxies move under the combined influence of large-scale expansion and local attraction. In voids, local effects are minimal. Galaxies move primarily under the influence of cosmic expansion, making them ideal tracers of how fast the universe is expanding. The expansion rate itself becomes more cleanly measurable when you remove the noise of local gravitational interactions. Void statistics also test cosmological models. The number, size, and distribution of voids depends sensitively on dark matter properties and the initial conditions after the Big Bang. Observing more or fewer voids than predicted would indicate problems with standard theory. So far, void counts match predictions reasonably well, providing evidence that current models capture the broad outlines of structure formation correctly. They get the big picture right, even if details like early galaxy formation remain problematic. What makes voids slightly unsettling is their extremity. The universe could have distributed matter more evenly. Instead, it created these vast, empty regions and concentrated almost everything into thin threads and dense nodes. The contrast emphasizes how gravity organizes space, pulling matter together and leaving enormous gaps. Within those gaps, any civilization that arose would see a very different night sky than we do. They would observe far fewer galaxies. Their view of the cosmos would be limited. They might conclude that the universe contains less than it actually does, having no evidence for the vast populations of galaxies hidden beyond their local void. Meanwhile, the light traveling through both voids and filaments undergoes a transformation that reveals just how far it has come. Every wavelength of light the most distant galaxies emit gets stretched by the expansion of space. Ultraviolet light becomes visible light. Visible light becomes infrared. Infrared stretches into far infrared and beyond. By the time these ancient photons reach our telescopes, their wavelengths have expanded by a factor of 14 to 16 times their original length. This effect is called redshift, and it's one of the most powerful tools in cosmology. The term comes from the fact that stretching wavelengths moves light toward the red end of the spectrum. Blue light shifts to red. Red shifts to infrared. The farther a galaxy sits, the more its light has stretched during transit, and the higher its redshift value. Scientists measure redshift using spectroscopy. Specific atoms emit light at precise wavelengths. Hydrogen produces a characteristic line at 121.6 nanometers in the ultraviolet. When astronomers observe this line shifted to 1,824 nanometers in the infrared, they know the light has been stretched by a factor of exactly 15. This indicates a redshift value around 14, which tells us immediately how much the universe has expanded since the light was emitted. When a galaxy with redshift 14 emitted its light, the universe was 15 times smaller than it is today. All distances were 15 times shorter, all wavelengths were 15 times compressed. Space itself has grown 15-fold since those photons began their journey. Here's where this becomes visually dramatic. The galaxy emitted ultraviolet and blue light from hot young stars. We see none of that in its original form. Every ultraviolet photon has shifted into near-infrared wavelengths. Every visible photon has stretched to mid-infrared. The entire spectrum has slid beyond what human eyes can detect. This is precisely why Webb uses infrared detectors. The telescope was specifically designed to observe light from the most distant galaxies, knowing that light would arrive in infrared wavelengths invisible to previous instruments. Hubble operated primarily in visible and ultraviolet light. It could detect some infrared, but not at the sensitivity needed to see faint, high redshift galaxies. Webb's instruments cover wavelengths from 0.6 microns to 28 microns, capturing redshifted light from galaxies at virtually any distance in the observable universe. But even as Webb confirms the extreme stretching of light, it has revealed a deeper problem with how we understand expansion itself. The universe is expanding, this is confirmed fact. But when scientists measure how fast it's expanding, they get different answers depending on which method they use. This discrepancy is called the Hubble tension, and it represents one of the most significant mysteries in modern cosmology. One method looks at the early universe. Scientists measure the cosmic microwave background, the faint radiation left over from the Big Bang. This radiation shows a pattern of hot and cold spots that reveals the universe's properties 13.8 billion years ago. From that pattern, they can calculate how fast the universe should be expanding today based on the laws of physics and the known composition of the cosmos. The answer comes out to approximately 67 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space expands by 67 kilometers per second. It's the expansion rate predicted by our best understanding of cosmic evolution. The other method looks at the nearby universe. Astronomers measure distances to galaxies using objects called Cepheid variable stars and Type Ia supernovae. Both serve as standard candles whose intrinsic brightness is known. By comparing how bright they appear to how bright they actually are, scientists calculate their distance precisely. Combining distance measurements with redshift measurements gives the expansion rate directly. This method yields approximately 73 kilometers per second per megaparsec. The gap might seem small, just 6 kilometers per second per megaparsec, but this difference is statistically significant and has persisted across multiple independent measurements. Both methods have been verified repeatedly using different datasets, different instruments, different analysis techniques. The cosmic microwave background measurements come from multiple satellites and ground-based telescopes. The nearby universe measurements come from Hubble observations spanning decades, now confirmed by Webb. Webb has verified Hubble's measurements using the largest sample of data collected over its first 2 years in space. The team used 3 different methods to measure distances to galaxies that hosted supernovae. All 3 methods agreed with each other and with Hubble's earlier results. Webb's measurements ruled out the possibility that Hubble made a systematic error. The tension remains. The early universe predicts one expansion rate, the late universe measures another. These cannot both be correct if our understanding of how the universe evolves is accurate. Several possible explanations exist, though none are fully satisfying yet. Maybe dark energy behaves differently than current models assume. Instead of remaining constant over time, perhaps its strength has changed as the universe aged. This would cause the expansion rate to differ between early and late epochs, explaining the discrepancy. Maybe there's some unknown physics affecting how light travels through space. Perhaps interactions with dark matter or other fields modify photon energies in ways we haven't accounted for. This could bias measurements in one direction or another. Maybe our measurements contain unrecognized errors. Perhaps some subtle systematic effect contaminates one or both methods. Scientists continuously search for such errors, but none has been found that could explain the entire discrepancy. The most intriguing possibility is that the tension reveals genuinely new physics. Perhaps the universe evolved in ways not captured by the standard model of cosmology. Perhaps additional forces or particles exist that influence cosmic expansion. Finding such new physics would revolutionize our understanding of reality at the most fundamental level. What makes this especially troubling is that the Hubble constant isn't just an academic number. It reveals how the universe has evolved over its entire history. It determines the universe's age, size, and ultimate fate. Getting it wrong means misunderstanding the cosmos at the largest scales. And speaking of large scales, we need to address something that had only been theorized for decades until recently: the direct detection of dark matter on cosmic Webb filaments. Dark matter makes up 85% of all matter in the universe. It doesn't emit light, it doesn't absorb light, it doesn't interact with electromagnetic radiation at all. We know it exists only because of its gravitational effects on visible matter. Galaxies rotate too fast to be held together by the gravity of their stars alone. Galaxy clusters move in ways that require far more mass than we can see. The cosmic web wouldn't exist without dark matter providing the scaffolding. For decades, scientists theorized that dark matter should line the filaments connecting galaxy clusters. Mathematical models showed it clearly. Simulations demonstrated how dark matter would flow along these threads, creating channels where ordinary matter would follow. But nobody had directly observed dark matter on the filaments themselves until now. Researchers used gravitational lensing to study the Coma Cluster, a collection of over 1,000 galaxies located 321 million light-years away. When light from distant galaxies travels past a concentration of dark matter, the dark matter's gravity curves space, causing the light to follow a curved path. This creates distortions in the images of background galaxies. Their shapes appear stretched or warped. By carefully measuring these distortions, astronomers can map where dark matter concentrations exist, even though the dark matter itself remains invisible. The team detected dark matter along the terminal segments of cosmic Webb filaments extending from the Coma Cluster. These terminal segments are the thin threads connecting the main filament to individual galaxies, the finest structure of the cosmic web. Previous observations had seen dark matter in the main filaments and at the nodes where filaments intersect. This marked the first detection on the smallest threads of the web, confirming that dark matter genuinely pervades the entire network. This discovery validates theoretical predictions about how the cosmic web organizes space. Dark matter doesn't just concentrate at nodes, it creates a continuous structure spanning the universe. Galaxies don't drift through empty space, they slide along dark matter highways that guide their motion. And if the cosmic web is more densely populated than we thought, the total number of galaxies in the observable universe might be far higher than previous estimates. For years, astronomers estimated the universe contains approximately 200 billion galaxies. This number came from Hubble surveys that counted galaxies in small patches of sky, then extrapolated to the entire observable sphere. The calculations seemed solid. Multiple independent surveys agreed. Webb has forced a revision. The galaxy density in Webb's deep field significantly exceeds what Hubble's surveys suggested. If these deep field observations are representative of the universe as a whole, the total number of galaxies could be trillions rather than hundreds of billions. Think about what this means. Every estimate of cosmic structure, every calculation about total stellar mass, every prediction about how many stars and planets exist, all of these depend on knowing how many galaxies there are. If the true count is 10 times higher than previous estimates, everything scales up accordingly. The implication for planets is staggering. Our galaxy alone contains approximately 200 billion stars. If each star has an average of one planet, that's 200 billion planets just in the Milky Way. Multiply by 200 billion galaxies, and you get 40 quintillion planets in the observable universe. But if there are actually trillions of galaxies, the number jumps to 400 quintillion planets or more. 4 followed by 20 zeros. The scale becomes almost incomprehensible. For every grain of sand on every beach on Earth, there might be 100 planets out there in the cosmos. That's the revised scale we're contemplating based on Webb's observations. The increase in galaxy counts comes from Webb's ability to see fainter objects than Hubble could detect. Many galaxies that appeared as faint smudges or weren't visible at all in Hubble images show up clearly in Webb's infrared observations. Additionally, Webb sees galaxies hidden behind cosmic dust that blocked visible light but allows infrared through. Entire populations of dusty star-forming galaxies, previously invisible, now reveal themselves. What remains uncertain is whether Webb's deep field observations truly represent average galaxy density. The telescope has observed relatively small patches of sky in extreme detail. Perhaps those patches happen to be denser than typical regions. Perhaps the galaxy distribution varies significantly across different areas of the observable universe. Scientists are working to answer this by conducting surveys of larger sky areas at somewhat lower depth. If those surveys show similar galaxy densities to the ultra-deep fields, it confirms the higher total count. If density decreases in wider surveys, it suggests the deep fields overrepresent the true average. Early results favor the higher density. Multiple deep field observations in different directions show consistently high galaxy counts. This suggests the abundance is real, not a statistical fluke from observing an unusually dense patch of sky. The philosophical implications are profound. If trillions of galaxies exist, each containing billions or trillions of stars, each potentially hosting planets, the probability of other life existing somewhere becomes nearly certain. The cosmos is so vast, with so many opportunities for chemistry and evolution, that Earth being unique seems implausible. The sheer number of possible sites for life makes the existence of other civilizations not just likely, but almost inevitable. Yet all these trillions of galaxies exist in the observable universe alone. The total universe extends far beyond what we can see. Some models suggest it might be infinite. If so, the number of galaxies isn't trillions, it's literally infinite. An endless expanse of stars and planets and possibilities stretching forever in all directions. We occupy one planet circling one star in one galaxy among potentially infinite galaxies. That's not insignificant. That's our home, our origin, our context. Webb has revealed just how large that context truly is. The universe is bigger, more complex, and more magnificent than we ever imagined. And we're privileged to live in an era when we can look out and see it, understand it, measure it, and marvel at our tiny but precious place within it. The observations continue. Each new image from Webb rewrites another page of cosmic history. Each spectrum analyzed pushes our understanding deeper. Each discovery raises new questions while answering old ones. We thought we knew the universe's scale. We were wrong. We thought we understood how galaxies form. We were wrong. We thought we knew when the first structures appeared. We were wrong. But being wrong in science isn't failure, it's progress. Every correction brings us closer to truth. Every revision refines our picture of reality. The universe is revealing itself to us in unprecedented detail, and what it's showing us is more extraordinary than anything we predicted. The cosmos is 93 billion light-years across in what we can observe. Beyond that, it extends farther, possibly infinitely. We occupy one planet circling one star in one galaxy among trillions. Yet from this tiny vantage point, we can peer across space and time to witness the birth of galaxies, the death of stars, and the architecture of reality itself. That's not insignificance. That's wonder. That's the privilege of being conscious beings in a universe that can be understood, measured, and appreciated. Webb has given us new eyes to see creation. What we're seeing demands humility, inspires awe, and reminds us that the universe is far stranger and more beautiful than we dared imagine. The true scale of the universe has been revealed, and it's only the beginning of what we're going to discover.